Yeah. How are you?
How are you?
Yeah. You're fine?
Yeah, I'm fine. How are you?
I'm fine. I'm fine.
Great.
Okay. So let's start with the class.
Yeah, sure.
Okay. Can you see my screen?
Yes.
Okay. So we have started about this converters. Okay. I think you remember buck boost converters.
Yes, yes.
Yeah. So we have explained the equations of output voltage
Yes.
and
For
we have
all.
explained the diagrams. Okay.
Yes.
We've explained the applications little bit.
Yes, but I have one question.
Yeah. Tell me.
Can you please write the formula of V input and V output for the buck boost converter? It was V output over V input equals to minus D over
Yeah.
1 minus D, right?
Yes. Right. Right.
Yeah, my question is,
Uh-huh.
uh, when you teach me about the buck boost,
Mm-hmm.
the answer should be in minus, but how is it not in minus?
Yes. Actually, we have to take the magnitude, basically, in case of buck boost.
Okay.
So the equation of V naught by VG, I have written minus D upon 1 minus D, right?
Yes.
But we'll consider here the absolute value. So if we take the absolute, what it will be? D divided by 1 minus D, right?
Yes. Oh,
So
okay.
So you will get the positive value.
Okay, great.
Okay. So let's begin with the class.
Sure.
Yeah. So I think I have told you something about CCM
And
and PCM. Do you remember?
yes.
So
Yep.
this thing, no doubt I have told you, but I haven't like totally explained you like
Yes.
how the circuit will behave in CCM and when it will behave in DCM. Okay.
Yes.
So for that, first I'll begin with the circuit, the graph. Okay.
Okay.
Yeah. This is the graph for the inductor current.
Okay.
We mainly study the CCM and DCM in case of the inductor current.
Okay.
So this is the I max, that is the maximum value,
Yes.
and this is the minimum value.
Okay.
So now what it will be I max?
The minimum value is in minus.
Yes, the minimum values might be in minus.
Okay.
As
Oh,
for this graph,
what?
I'm telling you look
Yeah.
for this graph. Okay.
Yeah. Why is it in minus?
I am considering suppose. Okay. This is
Okay.
zero. Okay.
Yeah.
This line is zero and inductor current is getting negative. Suppose the current is going negative direction also. I am considering both positive and
Oh,
negative
okay.
cases.
Okay. Okay. Yes.
Okay.
Yes.
Just consider it. Okay.
Yeah. Not negative value, just the negative direction, the other direction.
Yeah, the direction of that, just consider the direction. Okay. So what it will be, the maximum current I max will be equal to IL plus delta IL by 2. Okay.
Why?
This is the delta IL, that is the ripple part from here to here.
Yes.
And the straight line indicates the average current IL.
Okay.
So we are considering only the maximum part, that is IL plus delta IL by 2,
Okay.
half. Okay.
Yes.
Now we'll consider the minimum current.
Okay.
It
Why?
will be
Why is it by two?
because it's considered as half. See, this is if I consider the complete triangle. Okay.
Okay.
This is the half, right?
Oh, so the one in the bottom is the IL, and the one at the above is the delta L.
Yeah, this is this IL and up to this is the delta L by 2. I have divided into like two parts. Okay.
Okay, now I understand.
Understood?
Yes.
Hmm. This is like the delta L by 2.
Yes.
So now for the minimum part, it will be IL minus delta L by 2.
Yes.
So what is the condition for CCM for the converter? Okay. To be in CCM,
Okay.
the minimum current of the inductor should be 0.
Okay.
This is the condition.
Okay.
So now, what is I mean? Suppose we are determining for the three cases. So first we'll consider suppose the buck. Okay.
Yes.
First we'll consider for buck. If I consider for buck, I mean is equal to IL. IL will be equal to I naught for buck. Okay, the output current. Okay. And delta IL, the equation, if you look at the previous lecture, I
Yes.
have find out the derivation to be V naught 1 minus D by 2 of Fs into L.
Yes.
So for I mean to be 0,
I
I
not should.
naught will be equal to V naught 1 minus D by 2 FSL.
Yes, but I have a question. Why
Yeah.
I meant should be zero, so CCM will be for the competitor to be in
Yeah.
CCM.
See, this circuit you can see
Yes.
in case of this the circuit to operate in CCM, the minimum current should not go to the negative value.
Okay.
It should reach to the 0 and again it should go up. Then it
Okay.
should go to the 0 and again it should go up.
Why? What is CCM?
CCM is the continuous conduction mode.
Yes, I remember that, but I didn't
Yeah.
really understand it.
Why means see the circuit whichever we are designing.
Yes.
Okay. Mostly we operate in this CCM.
Nice.
Now, why we required only this mode? Because in order to drive the circuit for a certain kind of application, okay,
Yes.
like we want the EV,
Yes.
like we want the motor, we
Yes.
want the current to remain in a positive mode, basically. It should not change the direction and come to the negative mode.
Okay.
So for that, we require the CCM operation. If the circuit goes to the DCM mode, then you will not get the desired output. There might be some errors you will find, okay?
Okay.
So now, what is I naught? I naught equal to V naught by R equal to V naught 1 minus D by 2 of Fs into L. This V naught and this V naught will be cancelled.
Yes.
Now this L is basically the L minimum, which is equal to R of 1 minus D 2 of Fs.
Yes.
This is the minimum inductance value. Okay.
Yes.
Minimum inductance value for CCM. So whatever will circuit design, suppose we know R 10 ohm. We need to operate duty ratio, suppose maximum 0.6 or 0.5. We know the switching frequency 15 kilohertz. Okay.
Yes.
By putting the values, we'll get an L minimum value. So we need to put that L value in our circuit. If the L minimum value exceeds, then the circuit will operate. And if it is less, suppose minimum value is 2 millihenry,
Yes.
and we got it, and we are putting in the circuit as 1 millihenry. Now there is a chance that our circuit will be in DCM.
Okay.
So in order to avoid that, we use this condition. Now we need for the boost, same process we will follow. I mean equal to IL minus delta L by 2 equal to I naught upon 1 minus D minus V naught. That is the equation for the delta L for boost. DTS upon twice of L for I minimum equal to 0. The value of I naught 1 minus D will be equal to V naught 1 minus D DTS by 12. So I naught, we can write V naught upon R into 1 minus D equal to V naught upon 1 minus D DTS by 12. So this V naught will be cancelled. Now we'll get the value of L minimum to be D 1 minus D whole square into R upon 2 of F. Okay. This is the minimum inductance value.
Okay.
Now we need it for buck boost. The same we will follow. I minimum, what is I minimum? Equal to IL minus delta IL by 2 is equal to minus I naught into 1 minus D minus. So since this is in minus, okay,
Yes.
so the sign will be plus
Yes.
1 minus D twice of Fs into L. So for I mean equal to 0, what you will have this minus sorry, I naught 1 minus D will be equal to V naught 1 minus D 2 of Fs into L, substituting the value of V naught upon R by 1 minus D equal to V naught into 1 minus D by 2 of Fs into L. So in our case, the L minimum will be, we cancel out this 2, 1 minus D whole square into R divided by 2 of Fs. This is the minimum inductance value. So whenever we'll design the circuit, we require these 3 important conditions for designing of L. If we do not follow this, there is a chance that our circuit will be in DCM. Okay.
Okay.
Up to this, I needed to explain because I have told you that I will be explaining this. Now
Yes.
we'll move further. What we'll discuss today, basically, we'll move to the part of modeling.
Okay.
Do you know modeling?
No.
And by the term model, what do you know model?
Uh, like put the circuit in the best shape or something.
Yeah. Model means any kind of model, circuit, base.
Yes.
So modeling will be how you model the circuit, the pattern, the way is called the modeling, the process. Okay. So I am going to first show you the diagram. Yeah. What do you understand from this circuit?
Uh, the
Any idea what is going on?
it's like checking if everything is correct.
Mm-hmm.
So we have V input, and then the V output goes back to the V reference. So
Mm-hmm.
do a check. If the
Mm-hmm.
volt is not what we intended, if it's less,
Mm-hmm.
uh, mm, rise the voltage. If the voltage is more, it will decrease it,
Mm-hmm.
I
Okay.
think.
This is basically the circuit. Okay.
Yeah.
So we have to model the circuit in such a way that our we need to find out what is the output and how to compare it with the reference. So this dynamic model of a circuit, maybe converter or any type of circuit,
Yes.
has two types of representation.
Okay.
One is called the state space representation,
Yes.
and another is called transfer function representation. Have you heard?
No, none of them.
This state space, it is called the modified or modern control system,
Yes.
and transfer function is considered as the classical control system. So we require both of the method, both of the designs or any one of the designs, so that we could apply our control to get the desired output, which will be putting it into the electric vehicle or motor. Okay.
Okay.
So in order to do that, this DC-DC converter needs to be modeled properly.
Yes.
So now comes, what is the state space representation? Just I need to begin with an simple example, like x dot equal to ax plus bu, y equal to cx plus du. Have you seen this kind of form?
Not that I remember.
You have not seen?
I have seen, but I don't remember it.
Okay, no problem. These are called a state space representation. Okay. So whatever circuit we have to represent it in this manner, where
Okay.
X are called the states, U is called the inputs,
Okay.
A is called the state transition matrix, B is called the input matrix,
Okay.
C is called the output matrix,
Okay.
and D is called the transformation matrix. So now I have represented in this way. Now I want to design it in a suppose, see, this is the circuit I got, but I need to do it in MATLAB, right? In Simulink.
Yes.
Just writing this in Simulink, it will be difficult to calculate. So
Okay.
what we will be representing it in block diagram form.
Okay.
So suppose x dot is the output, right?
Yes.
Then this is the x dot, suppose. From x dot, how will we get x? Tell me.
If it what?
X dot is there.
Yes.
Now we want to get X. How will we get? What we have to do?
Is it X not
Get X back.
it's X not square?
No, no, no. You tell me what do you mean by X dot? Equal to what?
I remember X dot, but I forgot. I have studied it, but I forget what does it mean.
Okay, okay. X dot is dx by dt.
Yes.
Differentiation with respect to time.
Okay.
So this is differentiation. So in order to get back to the same position X, we have to integrate
Yes.
X.
So
So we'll getting X back. Okay.
okay.
So here we'll integrate it. Fine.
Fine.
Now what is X dot? X dot equal to AX plus B into U.
Yes.
Now I'll put a summation here. Now in this summation we have B matrix and it is fed by input to the system. Now X dot equal to what? AX plus BU. We got the BU part. Now we need the AX part. So what will I do? I'll take another blocks which I consider the A and I will add with the BU part.
Okay.
From here we got the AX plus BU. This is the plus summation. Okay, we got
Yes.
the X dot. Now this part we have done. Now we need the Y part. Y is what? Y equal to CX plus DU. That is, we will again multiply with the gain C matrix plus du. So we require a summation here plus d into u. So from this part, there will be a d matrix which will come till here.
Okay.
This is the plus, and this is y. This is the AX part. Is it clear? You check once.
Yes.
This is the way in which we have to represent it in MATLAB symboling form, the equations. Fine?
Yes.
Okay. So now I'll I'll show you the circuit now. Okay. Suppose a circuit is there. Okay. This is a
Okay.
circuit in which a resistor is there, a capacitor is there. Now we have to represent it in the state space form, that is X dot equal to AX plus BU. What we have to do? First, we have to follow the steps. What is step one? Step one will be we have to identify energy storing elements. What is energy storing elements? Any idea?
Uh, Energy storing? You mean like inductors and stuff like that?
Yes, yes. Energy storing elements will be inductor and capacitor. So here
Okay.
in this case, energy storing element is only one. That is C. What is step 2? Step 2 will be identify the variables that will be used for modeling. We have to identify the variables used for modeling the circuit. So in this case, the energy storing element is capacitor. So our state will be the voltage across the capacitor VC. And input we know is the input voltage VG. What is step 3 next? Step 3 will be we have to obtain the differential equation. Using KVL or KCL. So in the above circuit, what will we do? We will connect a load here, suppose. So here the I0 current will flow. So what will be the current IC? IC will be equal to IR minus I0.
Yes.
Suppose I consider this as IR.
Yes, it will be because of KCL, right?
Yeah. IC will be equal to IR minus I0, where IR will be equal to VG minus VC by R, and I0 is equal to VC upon R. This is suppose R and this is R0 we are considering. Okay. So now we'll write this equation in terms of the current across the capacitor. What is IC equal to CdVC by dt? Equal to Vg minus Vc by
Yes.
R minus Vc by R0.
Yes, yes.
What is dVc by dt? Will be equal to 1
All
by
okay.
CR,
Yes.
right?
Yes.
Vg minus Vc minus 1 by CR0 into Vc.
Yes.
Now we have the last step 4, that is separate it in the form x dot equal to ax plus bu. What is x? I said x, I said it is Vc. So what it will be? X dot will be Vc dot equal to dVc by dt. Okay.
Uh, okay. Okay.
X, I said the state as the energy storing element Vc, right?
Yes.
So x dot will be Vc dot.
Yes, yes.
Yeah, it will be dVc by dt.
Yes.
So now I'll write it in this form, that is x dot will be equal to dVc by dt equal to, since I need to write it in A form. A is a matrix. So I'll take this. This. What is X? X is VC. Okay.
Okay.
So now if suppose this equation, okay, equation number 1, I need to actually expand it from from 1 dvc by dt equal to 1 by CR into Vz minus 1 by CR into Vc minus 1 by CR naught into Vc. I have just expand this equation. So now this part will what? Will take suppose common, that is minus 1 by CR minus 1 by CR naught into Vc plus 1 by CR into Vz. So we have to take dVc by dt in terms of Vc, right? This is what our objective. So what is in terms of Vc? Minus 1 by CR minus 1 by CR naught plus we need U. What is U? U is in this case Vz, which is the input voltage, which I have already mentioned it here. So next matrix will be B matrix, which will be equal to 1 by CR into Vz. Now, what is Y? Y is the output voltage.
Yes.
V naught equal to Vc. So these two are the equations. This is the straight transition matrix. Actually, this is the process like I showed you how to do. Actually, like very detailed explanation is also required. I have just shown you shortcut so that you'll get some idea. Otherwise, it is difficult, right, to understand. I just gave you some idea like how to do it so that you can, if your professor will ask, you can explain like what is the energy storing element, how you choose the state. Okay.
Okay.
Yeah. So moving forward, we will go to buck. What is the circuit of buck? I think you know. The circuit of buck is this one. Then we have a MOSFET. Then we have a diode. Then we have inductor. Then we have what?
Capacitor, then the load.
Capacitor, load, and then it is finally connected it here. This is suppose VG, L, C, R. Okay. So the whatever our DC-DC converter circuit is there, it operates in two switching mode, on and off, right?
Yes.
So in terms of on, we write dt. I think I have explained you. And in terms of off, we write 1 minus d into t. Okay, remember?
Yes.
Hmm. D is the duty cycle. So during the on time, it will be duty, the dt. During the off time, it will be 1 minus dt.
Yes.
So we need to draw the circuit for dt, that is for the on time. I'll moving this fast as you already know these things.
Yes.
So while we solve the equation, sorry, we'll get L dIL by dt equal to Vg minus Vc, and C dVc by dt will get IL minus Vc by R. You can ask me if you find any doubt, okay, in between.
Okay.
As you already know, so I'm moving this fast. So now I'll write this on equation in terms of our state space model. What is our state space model? What is, you tell me, what are the energy storing elements here?
Capacitor and inductor.
Yeah. Now I'll write the state space equation, that is in terms of x dot equal to ax plus bu, right? I'll write in this manner. Okay.
Yes.
So what will be our x?
X will be and then integration of AX plus BU.
X will be the energy storing element IL and Vc.
Okay.
Okay. The current across the inductor and the voltage across the capacitor. Okay.
Okay.
So now I'll write it in the form of equation. What is x dot? X dot will be IL means what? dIL by dt. X
Yes.
dot.
Yes.
X dot will be dIL by dt. Just try to understand. Is it clear?
Yes.
Okay. So x dot I'll write is suppose IL dot and Vc dot. You tell me if it is clear. I'll write in the form of this. So first I write x dot. X dot is equal to IL dot, that is dIL by dt, and Vc dot. Okay.
Okay.
Now I'll write this IL dot. IL dot means what? dIL by dt. IL dot means what? dIL by dt. Vc dot means what? dVc by dt.
Yeah.
Okay. Understood, right?
Yes.
Yeah. So now we'll write it in terms of IL and Vc. So dIL by dt in terms of IL, tell me what will be the value?
Of what?
DIL by dt, that is, this is IL dot means what? DIL by dt.
Yes.
So in terms of IL, is there any IL involved here?
No.
Yeah. So in terms of IL, DIL by dt will be 0.
Okay.
In terms of DIL, in terms of Vc, what will be DIL by dt? Vc?
Uh, will it be zero?
No, VC is there, right? This is VC.
Oh, yes.
It will be minus 1 by L,
Okay.
because this L will come here. Okay.
Yes.
If the L will come at the bottom, so it will be what? VG minus VC by L. So that means what? Minus 1 by L into VC.
Yeah.
Yeah. Now I want you to tell this one. What it will be VC dot, that is dVC by dt in terms of IL.
What is what?
dVC by dt, that is VC dot, okay, in terms of IL, what it will be. See from this equation.
Yeah, there will be, so it will be IL.
IL is there. What will be the coefficient? Before IL, there will be something.
Not one,
1, 1
over.
by C.
Yes,
This C will come down, right?
yes.
Yeah. What it will be in terms of VC?
1 over, minus 1 over C by VC.
Minus 1 upon RC.
Yes,
R is there, right?
yes.
Yeah. Plus, there will be some input, x dot equal to AX plus B into U. So now, in terms of VG, dIL by dt is equal to 1 by L, right?
Yes.
And in terms of dVC by dt, there is no VG, so it will be 0. Clear?
Clear.
Now, going to the output part, the output voltage V naught,
Yes.
again in terms of IL and VC, in terms of current, it is 0. In terms of output voltage, will be equal to capacitor voltage, it is 1. Okay.
Okay.
So this part we have drawn the DT part. Plus B1U Y equal to C1X plus D1U. DT part we have done. Okay.
Okay.
Now we'll consider the 1 minus dt part. That is the off condition. So for this, we require the circuit for the off condition. The off condition circuit will be writing the equation, it will be dIL by dt equals to minus VC and C dVC by dt equal to IL minus VC by R. Same, we have to form the differential equation also in this case. So tell me what it will be A matrix. In terms of IL, what will be IL dot?
IL dot will be 0.
Yes. In terms of VC, what will be IL dot?
1 minus 1 over L
Yes. In terms of dvc by dt, in terms of IL, what will be dvc by dt?
will be 1 over C
Yes. What will be vc in terms of vc?
minus 1 over L RC.
Yes, correct. So these are the two equations we got. So
Okay.
now we'll writing in terms of 2x plus b2u c2x plus d2u. This will be 1 minus dt equation. Okay.
Okay.
So now what we have in this circuit, okay, and whatever like we'll get the circuit, the values of the current,
Mhm.
voltage. Okay, just wait. This I'll write it as equation number 1. Equation. Okay. Sorry. One more thing I forgot. What will be in terms of the input VZ, DIL by dt in terms of VZ?
VG, wait, 0?
0. In terms of VC, dVC by dt?
0?
0. Yeah. So this I'll write equation number 2. So now in a converter, we have the current and the voltage. Okay. So those current and the voltage will have two components. What are the two components? Like the current, we write it as IL, right? And voltage, suppose we write it as V, right? This current is called the large signal. Okay. Which will have two components, that is two parts. What are the two parts? One is the steady state part and one is the variation or the small signal part. Okay. Because whatever, like suppose whatever circuit, suppose this is the current, it is going in this ways. Okay. So the current will have something called the steady state part, right? That is the constant part. And also it will have the variation part. So these two things are clubbed together to form this large signal part. So whenever we do any kind of derivation, okay, like we are designing the circuit here, we're modeling the circuit. So we have to consider these two components. If we do not consider, then it will be difficult for us to get the actual result. So voltage will also have this V part plus the variation part. These two components are important, right?
Correct.
Yes. So now from the circuit 1 and 2, we got the two models. Now we have to consider the variation part. Okay, the variation part is important. Before that, we know that the circuit is operating in on and off mode, right? So those on and off mode is very important.
Okay.
So how to write the circuit in terms of on and off mode? I think you remember in the previous class, there is the on, there is the off, then we combine the two circuits together. Do you remember? Suppose
Yes,
this is
for
the this
yes,
is the this is the on part, right?
yes,
So on part will be what? DIL by dt will be equal to 1 by L. Okay. D, suppose I consider D as the on part, VG minus 1 by L D into VC. This is for the on, the DT
yeah,
part.
yes,
Okay.
yes.
Where I am not writing the T, it is not required actually.
Right.
Now for the off part, the same. Where is the off part? This is the off part. It is DIL by dt equal to minus 1 minus D by VC by L.
Yes,
Minus 1 by L, 1 minus D into VC by VC.
yes,
So we need to do the averaging. What I said, averaging. Averaging means what? These two will be added together.
yes.
So if we add together, what will you get?
Uh,
DIL by dt will be
yes,
equal to, this will be same,
yes,
1 by L D of VZ.
yes,
Now this minus 1 by L D into VC plus this what? Minus 1 by L. I'm just some space is less, but I'm writing it in small. D into VC. Now this minus 1 by L VC. This minus minus plus 1 by L D into VC.
yes,
So this minus this plus. So this two will be cancelled.
yes,
Now we will have what? Only this and this left.
yes.
This is the, what I mean to say, the averaging part. Okay.
Okay.
So this part we have to put in the equation, state space equation that we have derived just now.
Okay.
What are the two equations we have derived? This is the on part
Yes.
and this is the off part. Now both the two combined, we'll write it in the averaged form.
Okay.
So what will be the average form? The average form will be IL dot VC dot zero minus 1 by L 1 by C minus 1 by RC ILVC plus D by L 0 into VZ. Fine. This is the combined part that I have written.
Yes.
Now we'll consider the two components, that is the steady state and the small signal, both. So what I said, what will be the IL? IL will be equal to capital IL plus small IL hat. This dot is there. What is VC? VC will be capital VC plus small VC hat. This dot will be there. You see this part. I need to consider both the part, the steady state part and the small signal part. Okay. So this I have written in this manner. So now I'll write the A matrix also in this manner. 0. So here there is not any variation. So directly I'll write the constant part minus 1 by L. Here also the constant part 1 by C. Here also constant part 1 by RC. Done. We don't have any problem. Now in this case, we have again the variation part. Again, in this case, we have D plus D hat by L 0 into VZ plus VZ hat. Now, if we write it in the large signal model, we have to follow some conditions. What are the conditions? The conditions are that whenever two small signal are multiplied together, then we can neglect it. That is the first condition. What is the number 2 condition? The steady state. Steady state means what? The constant value. Steady state means constant value. So now what will be the, suppose 4 is a constant. So what will be the derivative of 4? Derivative of 4? It will be 0.
Yes.
Yeah, the constant value derivative is 0. So the capital X is the steady state part. So the derivative of this capital X, sorry. Derivative of capital X will be 0. These are the two conditions. So now this equation number 3, we will separate because here it is containing the both part, the steady state and the small signal. We'll separate this. That is IL dot and VC dot plus IL hat dot VC hat dot. Next, we'll separate in terms of the current and voltage values also. That is 0 minus 1 by L 1 by C minus 1 by RC. See what I am doing right now. This is the main equation I got. Okay. From this main equation, we will separate this part, this part, this part, this part, then the steady state part and the small signal part. We have to separate it. So now I'll write the steady state part first. I, L, VC. Now same I'll write it in case of the small signal part. Now this part is done. Now for the input part, once this will be multiplied with this, both way we have to do. That is once d by L by 0
Yes.
will be multiplied with Vz plus d by L by 0 will be multiplied at Vz hat plus next the small d hat by L into 0 will be multiplied by capital Vz and small d hat by L into 0 will be multiplied by small Vz hat. We have done. Everything is done. Okay.
Yes.
Now we have to follow these conditions. What is the condition say? That if the two variations are multiplied together, then you can neglect it. Okay. So you see, in this case, we have the constant, no problem. We have constant and one variation, no problem. We have constant, steady state, steady state. We have steady state, small signal. We have small signal, constant, no problem. We have small signal, small signal. So these are multiplied together.
Yes.
So now this will be 0. Next, what is the condition? The derivative of the steady state part will be 0. So what is the steady state part? The steady state parts are this, this, okay, all steady state. This is not steady state because small signal part is there. This is the steady state part and not. Only these are the, which are the steady state parts? Those will be 0. Then this is 0. Then this will be 0. This will be 0. Now what we have left? We are left with the equation on Vg hat plus d hat by L0 upon Vg. Now we'll again try to make it easier to understand. We take the variations d by L, then Vg by L 0 0. In terms of matrix, we are taking it as Vg hat and d hat. So this is our final equation.
Okay.
See, it's kind of little bit long, but for modeling to understand properly, you need it.
Yes.
It's kind of long. I think you might be bored a little bit.
Yeah, I'm not bored, but I am just a little bit confused of the all equations and stuff like that. That's all. But if I revise it, I will remember it.
Yeah, you just take a look, okay? You study.
Okay.
Yeah. Actually, I want to download the PDFs of this, okay? What I am
Yeah.
writing, but I don't know, it's not going good. Uh, what can I do? I can share a link, okay?
Okay.
If you open the link, you can directly get these things.
Okay, nice. Because I'm not. I won't be able to write all of this.
Yes,
To,
yes, yes. I understood. I understood. Whenever I
yeah.
try to download, see, whenever I try to download, I have one called file option. When I try to download, save as PDF, okay?
Yes.
But the file I can show you, it's not coming properly.
Okay.
What can I do? I'll share.
Yes.
Okay, I'll share. Then you can, I think, check it properly, the link. I'll share it with Agarwal, okay?
Okay.
Hmm. So now this is the standard form of the buck converter, the state space model. Now I need to convert it into the transfer function.
Yes.
That is also important.
Yes.
So what is transfer function? Transfer function is basically what? Laplace transform of the output upon Laplace transform of the input with initial condition 0. Okay.
Okay.
This they might ask you in Viva or like what is transfer function? Transfer function is the Laplace transform of the output by Laplace transform of the input with initial condition 0. So
Okay.
now this we need to find it out. So when there is a state space model, because we know the state space model, this is the A, this is the B, okay? And for C, basically we have just the output, that is the voltage V naught will be equal to 0, 1 in terms of IL and V's, no problem. This is the voltage C matrix. So whenever we have the state space form, to convert it into transfer function, directly we have a formula. What is the formula? The transfer function is C Si minus A inverse of B plus D. This is the standard formula of converting the state space model to transfer function.
Yes.
That if it is there, directly we can convert, no problem. So now, what is our objective? Our objective is to control the duty cycle. You see, I think I'll show you. Yeah, this model. In this model, we are getting an output voltage. We are comparing with the reference and we are getting some error. Can you see whether?
Yes.
Yeah, we are getting some error. So now this error, what it will do? The controller will check what is the error. Then it will give a desired control input. Now in our converter, how the converter knows which voltage to get? That is, suppose we are giving 10 volt and we want 5 volt. So what will the converter do? The converter will change the duty cycle. What will the duty cycle do? Suppose it is a buck converter. For 0.5 duty ratio, we'll get 5 volt from 10 volt. This is our objective. So now the controller will change the U, the control input, and based upon U, the duty cycle will change and we'll get the actual voltage, that is the required voltage.
Yes.
So from our study, in order to convert it into transfer function, we need what? The output voltage V upon any one of the input. What are the inputs? The inputs in this case are these two. This is A, B, this is X, this is U, right? So this
Yes.
U means input. So one input is this one and one input is this one. So what is VZ? VZ is the voltage, input voltage.
Yes.
What is D? D is the duty ratio.
Yes.
So what is our objective? To control the duty ratio
Yes.
so that we'll get the desired voltage. So we'll write the transfer function in terms of this duty ratio.
Okay.
Now we'll consider this as 0. We don't want this VG. We only want this D hat.
Okay.
So what will be our transfer function? C equals to 0, 1. What is S into I? S into I matrix will be like this.
Yes.
Minus A. What is A? A is this one. This will be inverse CSI minus A inverse into B. What will be B? B will be in terms of, we require only this D hat part. Okay.
Okay.
That means only this part we require. It is VZ by L.
Okay.
So it will be VZ by L into 0. So now we'll multiply together. What will be SI minus S? S minus 0 will be S. 0 minus minus 1 by LC will be 1 by L. 0 minus 1 by C will be minus 1 by C. S minus minus 1 by RC will be S plus 1 by RC.
Okay.
This will be whole inverse multiplied by this. Okay. So now we have to do this inverse. Now inverse means what? First, I need to find the determinant of this. Determinant means what? This into this I'll multiply and this into this I'll multiply. That means this into this minus this into this. So this into this, if I calculate, it will be S square plus 1 by RC into S, and minus this into this will be plus 1 by L into C. Whole bracket. Now for 2 by 2 matrix, there is a shortcut to find the inverse. Directly we switch these two numbers and change the sign of this 2. So it will be this one. Next multiplied by this. Now directly we will multiply. First this will multiply with this. Okay, matrix multiplication directly.
Yes.
It is what? 2 by 2 matrix. It is 2 by 1. We'll get 2 by 1 matrix. Okay.
Okay.
S plus 1 by RC into VZ by L. This into this 0. Again this VZ upon LC. Now finally our equation this. Now this part I'll take in the left side. Now I'll multiply this matrix with this. This is what? 1 by 2 This is 2 by 2. So we'll get it as 1 by 2. Yeah, 1 by 2. Okay. So first row into first column. That is 0 into this plus 1 into this. Okay, we get a single value only. That is VZ by LC.
Okay.
Okay. Sorry, this is so finally the equation is this one. And this is very important equation. Okay. I have derived it for you, but it takes so much time,
Yeah.
find out these things. And in the book also, you will not find properly.
Yes.
They will not explain you everything. So this is what the transfer function of Buck.
Great.
So if we apply this to like any kind of controller, we'll get the desired. If we change the duty ratio, we'll get the actual output.
Okay.
Directly, also what you can do, you can take it in MATLAB. Okay.
Yes.
Directly we put the value, suppose 10 volt, L you put any inductor, capacitor, then you write the transfer function. Okay.
Okay.
Then you multiply it with duty ratio. Suppose you give duty ratio as 0.5 and input VG is 10 volt. You check the output, you will get as 5 volt. In MATLAB, you can test. Okay. Later on, we'll do these things. I'm just telling you.
Yes, after
Now,
we the electronics part, we can go to the MATLAB and stuff like that.
Next, similarly, our explanation comes to the next part called boost.
Yes.
I think for Buck, you have explained understood most of the things.
Yes. Yes.
Okay. So boost, what I'll do, I don't need to require much, but I will go into the equations. Just check once. If there is any doubt, you can tell. Okay.
Okay.
Same for DT. We'll have a model. So here also we'll be writing in terms of IL and VC.
Yes.
So what will be the equation of IL dot in terms of IL?
0.
0. And VC in terms of VC dot?
0.
0. VC IL in terms of VC dot?
0.
0. In terms of VC dot?
Is it not? Oh no, no. It will be. Wait. Is it not zero?
No, it's not 0, correct. Because this V naught will be equal to minus Vc by R.
Yes.
So what we can write?
We can write one over R, minus one over R, I not.
Yeah,
Oh, C.
yeah,
Oh, yes.
correct. Okay. What about in terms of Vz?
It will be 1 over L
Mm-hmm.
and 0.
0. Good. So this part we have done. Next, we'll move to the 1 minus dt part directly. So now tell me what it will be IL dot in terms of IL.
0.
0. In terms of VC.
0.
No, VC it is there, na?
Wait.
IL dot in terms of VC.
It will be
IL
V,
dot in terms
VC,
of VC.
VC over L.
Minus 1 by L. This one.
Okay. Yes.
Okay. Yeah. What it will be VC in terms of VC dot. This I have to, for now, first tell me in terms of IL, okay?
1 over C.
1 over C. And what about VC?
1 over RC.
Minus.
Minus 1 over RC. Sorry.
What about VZ?
VG is 1 over L.
Mm-hmm.
0.
And this PC dot
0.
0, right?
Yes.
And the output voltage is as usual, we'll get the same 0, 1 in
Yes.
terms of IL and so we get the two equations. Now,
Yes.
what is our objective? Averaging. We'll do averaging. Averaging means what? We'll combine both the on and off conditions. That is, the A matrix will be equal to A1D plus A2 1 minus D. B matrix will be same B1D plus B2 1 minus D. C matrix will be C1D plus C2 1 minus D, and D matrix will be D1 D plus D2 1 minus D. Okay, that means on and off condition we'll consider all together,
Okay.
adding it up. You understood, right?
Yes.
Yeah, this is in just in terms of matrix. No, this is same like earlier when we add this to, this is also same, just matrix way we add in this way. I'm just have showed it like to you. Okay,
Okay.
just the same. So now If we want to write it in terms of equation, how will you write? We'll write the both the this part and the earlier part. Okay. That is what we have. The duty ratio D, the current IL is the steady state plus the variation part. VC will be VC plus VC hat part. Similarly, D is D plus D hat part. Similarly, VG will be VG plus VG hat part. So all these variations, that is the small signal and the steady state, we have to consider it to get a large signal. Okay.
Okay.
Okay. So I think today's time is over.
Yes.
So we'll continue again next.
Yes, I will talk with Agrawal to see the next meeting because I am not available this week.
Okay, no problem. No problem.
Yep.
Today you have understood, right?
Yes, today was very good. Yes, thank you.
Yeah, we'll getting in some details. Okay, some details because it is required, huh?
Yes, yes. And I think we're gonna continue 1 hour and a half class because it's much better.
Yeah, okay, no problem.
Okay.
Okay.
Thank you, brother. See you next time.
Okay,
Bye.
thank you. Welcome.
Bye.
Yeah.